been given a data set of this energy output, and what I have done is and we have to determine what model we can use to predict this energy output better. So since this is a linear data, we have the historical data available, and we have 4 features to choose from. I'll be going ahead with the multiple linear regression model. I'll be basically selecting or selecting and unselecting different features to try which one works the best. Since we don't need to classify anything, I'm not going to use logistic regression, and we don't want any highly complex model also. It should be an interpretable model, so that we can have so that when we have the weather estimates available, we can predict how much energy should be there in circulation, so the companies can predict it properly. So that's why I'm using multiple linear regression model, and the evaluation metrics I have chosen are like for outcome. I'm basically focusing on the efficient production and the usage of energy, so maybe lower cost per unit of energy and lower emission rate if we predict it right. And the output can be measured by mean squared error, mean absolute error, or mean absolute percentage error. Going ahead, I have so we have almost 9500 observations, and we have 4 features to predict one target energy and energy output. So I have divided that all the observations into test set and training set. Test set can be anywhere between 10 to 20%, so I have taken 15%, which is 1435, and total training set is the 85%, which is 8133 observations. Now out of that, I have divided it into again 15 and 70%. So I'm taking a fixed validation set approach and not a cross validation approach, because I'm using an Excel model, which is difficult to manually separate. So 15% of the validation set, which is 1435 rows, which is equal to the test set rows, and the final available training set is 6697 rows. So that's how I have divided in my training set, and validation set and test set. So now training set 1, I used data analysis of Excel, and I used all the 4 features together, and I got this model where coefficient is this, and different slopes of all the features are here. So my first model is this, where it's -2 temperature, minus 0.22 of V, plus 0.06 of pressure, minus 0.17 of humidity, and the coefficient of 454. So seeing this, I put my data in validation set. So y1 is this. I have predicted my model 1 values by just putting the values on y1 equation here, and here I got this result using the actual formula for MSE, MAE, and MAPE. I got these error values. Similarly, for model 2, I removed the pressure, because the value was very low, this slope was very low, so I removed that, and I got a new model considering only the first 3 variables, and this is the new R. It's slightly higher, the coefficients and intercept has also changed. I have again put these values in my validation set, and I got this result. Calculating this, the errors for model 2 are slightly lesser than model 1. Now I am removing another feature, which is the humidity, because this also had a lower coefficient, slightly lower coefficient. But on so in model 3 I got these values. Again I put those in my validation set, and my error values increased slightly. So although we can see M3 is better than M1, but M2 is still the best. Now I used all this data into my test set, and again I predicted all the values and calculated all the error rates. I still see that M2 is the best among all, because it has the lowest error. So yep, that's what I have described here. In model 1 all 4 features, model 2 only 3 features, and model 3 only 2 features, and out of that M2 is the best of all. um, so since the lowest cost function is minimum in M2, I select this model where the final features are temperature, V, and humidity. V is the vacuum, yes, sorry. Thank you.